Good morning. Lovely to be here, and I'm really happy to have a chance to talk to you for 45 minutes or so about one of my favourite topics, which is monsoons. So I'm a researcher and lecturer at Melbourne University, and I work on using climate models to look at variability and change mainly in tropical climate, so monsoons and so the South Pacific Convergence Zone, in present day and future climate, and also in paleoclimate as well. I haven't included anything on paleoclimate in today's talk because there's just too much to talk about if I try to cover the entire Earth's history as well as the present and future. So I just wanted to start by reflecting on the knowledge of Australia's First Nations peoples who have lived with and experienced and understood monsoon climates in northern Australia over many tens of thousands of years. And these are a couple of the beautiful seasonal calendars that were produced by traditional owners in collaboration with CSIRO and the Bureau of Meteorology. You can't see the details obviously, but they're available on the Bureau's website under the Indigenous Weather Knowledge link, and they show two communities, two different perspectives, I guess, on the wet season up north, basically looking at what happens with the weather, but also what happens with a whole lot of ecological indicators like plants and animals and things like that. So there's a lot of different ways of thinking about the monsoon, and I'm going to be focusing the rest of this talk on, I guess, the more traditional kind of Western science perspective, but I just wanted to start by reflecting on the incredibly deep and long knowledge of Indigenous people in this country. So I'm going to talk a bit about the global monsoon, and I'll explain what that means, and also some of the basic ideas about the physical mechanisms that produce the monsoon. I'll talk a little bit about regional monsoons, very briefly, mentioning each of those which we typically consider as part of the regional monsoons. And I'll talk a bit more detail about the Australian monsoon. I guess that's been the main focus of my own research, and also a few other people in this room, to try and understand that monsoon better. I'll look at the variability of the monsoon in terms of the shorter timescales, so the intra-seasonal, the bursts and so forth, as well as the longer timescale variability. And I guess I'm not explicitly talking here about weather systems, but we need to think about, what role weather systems are playing in variability on all of these timescales. And then in the last part, I'll comment a bit on how we think monsoons may change as the world warms, and what we've seen so far, and what some of the uncertainties are in terms of understanding future changes in the monsoon, in particular in the case of the Australian monsoon. So let's start with the basics. The word monsoon is usually attributed to Arabic. I've seen this word spelt many different ways, and I apologise for those of you that speak Arabic, but it's understood to be referring to the seasonal reversal of the winds in the region of the South Asian monsoon. So it's been studied and described for many hundreds of years in terms of the scientific community. Halley, back in the 1680s, proposed that it was the differential heating of the land and the ocean that drove this monsoon circulation. And then Hadley, of the Hadley cell, suggested that the winds were deflected by the Earth's rotation. And so you can see this map here, this sort of vectors here, I guess they're vectors, showing the curvature of the winds coming into the Indian region, and he noted that that was consistent with our understanding of the Coriolis effect. So these were very early observations, but let's just look at what we see when we look at the large-scale patterns of pressure and winds in the seasonal mean. So this is the January, the austral summer circulation, we can see in particular the sort of average position of the intertropical convergence zone, the ITCZ. And you can see that the ITCZ is displaced into the southern hemisphere in the peak austral summer season, but particularly over land, over South America, Africa and Northern Australia. In this season, we do see continental heating over land areas, which leads to low pressure, and we tend to see the development of moist onshore winds into those regions over land areas. It's not as clear in the southern hemisphere, though, as if we look at the picture over the northern hemisphere summer. And now we see a much stronger movement, seasonal movement of the ITCZ, in particular this very large northward shift over the Asian continent. And so we have, in the northern hemisphere summer, we have strong heating over land, particularly over the Himalayan region, very low surface pressure, and that drives that strong onshore circulation. At the same time, we have similar circulation coming into the region of the West African monsoon, and I think some of you have been looking at that in your chart discussion this week, and some of you have been looking at what's going on in terms of the Asian monsoon at the moment. So it's coming into the peak of the Northern Hemisphere summer monsoon season, and in all of those regions, this is just the kind of long-term average conditions. We expect to see the strong monsoon circulation and rainfall associated with that, although, as I understand this year, in some cases it's actually a bit drier than normal. So looking at the observed seasonal cycle of precipitation, this is just from the TRIM satellite data from 1998 to 2007, and we can see features that map onto the pressure and winds that we looked at previously. So we can see again the seasonal migration of this tropical convergence zone, as well as the stronger shifts in the Asian region, where we have the summer monsoon in July, and then southward shift of convection to the maritime continent and over northern Australia in January. Although you'll notice that it's really only the northern the northern top part of the continent that is really under that strong monsoon regime. Okay, so this is just a very kind of introductory summary of what we would see if we look at observations. And so if we go back to some classic definitions of what even is a monsoon, Ramaj put forward this idea of the monsoon, which is based on a number of criteria that focus on the circulation. A shift in the direction of winds between the peak summer and peak winter of at least 120 degrees. The wind has to be relatively constant in that direction in each season. The speed has to exceed 3 metres per second, and the pressure has some kind of steadiness criteria. So he's talking about having a kind of relatively constant regime in summer, which reverses in the winter. And you'll notice that none of those criteria actually relate to precipitation, which is interesting. So there's some debate back and forth, but basically he argued that the monsoon needs to be characterised by the circulation rather than the rainfall regime. And when you use that definition, you end up with this region within the contour broadly fitting that criteria as the classic monsoon region. More recently, others have come up with different definitions. There's some interesting work by Ben Wang and colleagues. They've looked at decomposing the monthly precipitation using EOF analysis, and they find that the first EOF is what they call the solstitial mode, basically the mode that lines up with the timing of the solstices, so summer and winter. It has this kind of pattern, and if you look at this paper, Wang and Ding 2008, they also show the second and third EOFs, and the second EOF is an equinox mode that sort of takes the residual in terms of the rainfall variability that follows in autumn and spring seasons. But they then use this to define a monsoon precipitation index, which is the ratio of the annual range, so the wet season minus the dry rainfall, to the annual mean. And so when that index, that MPI, is larger than 0.5 and the annual range is greater than 300 millimetres, they then classify that as being within the global monsoon domain. So this is that black contour here. And that definition has sort of been modified by some subsequent work to, for example, one that's used here, where we have summer minus winter exceeding 2 millimetres per day, and summer accounting for at least 55% of the annual total. And then we end up with the regions within these purple contours as being part of that global monsoon. So you can see that here we're focusing on the precipitation seasonality rather than the wind reversal. Sometimes there's a combined definition which requires both wind reversal and the rainfall component, but in this case it's just the rainfall. And I wanted to also just mention the definitions used in the IPCC report that came out a couple of years back now, where they define the global monsoon as the area where the annual range is greater than 2.5, and so that gives them all of these areas inside the black contour. But then when they talked about the regional monsoons, they actually decided to not include all the ones in the polka dots. So these regions are considered to have strong seasonal rainfall, but not really fit the characteristics of a regional monsoon, and they're not usually studied by the climate science community as being regional monsoons. So they had individual sections in the report that focused on the North American, South American, West African, South Asian, East Asian, and this Australian maritime continent monsoon, which was actually the one that I was involved in writing, but they sort of didn't include these polka dotted areas. So let's think about what is actually driving these large-scale monsoon circulations. There's usually a number of key mechanisms that are identified. In the first three are usually kind of listed together. So we have a seasonal oscillation of solar heating, which drives the differential heating of land and ocean and produces that resulting pressure gradient. And so that was the one that Haley identified, and we'll spend a moment going through each of those in a bit more detail. Then, in addition to that, the actual wind direction is determined by that rotational effect of the Coriolis. And thirdly, Peter Webster contributed the idea that we need to include the effects of latent heat release, diabatic heating from moist convection to fully understand the monsoon circulation. So those three criteria are often sort of grouped together in the classical understanding of monsoon circulation, but the fourth one has been more focused on in recent times, and that's the idea of the seasonal migration of a tropical convergence zone. It was first discussed quite a long time ago, but it's been the focus of a lot more recent research, and I'll talk about that as well in a moment. So let's start with our differential heating and pressure gradients. So we have, in the summer season, I guess we could think of this as the Asian continent at the moment. We have strong summer heating, and that's leading to the expansion of the warm air above that land surface and higher pressure surfaces over the land, which then end up sloping downwards over the cold surrounding ocean. And so we have a pressure gradient force which drives the transport of air towards that cooler ocean at height, and then that drives basically a low pressure over the land surface, and therefore we have a return flow at the surface of the onshore monsoon winds. And to maintain continuity, we have then a full three-dimensional circulation driven by the low level and upper level pressure gradient forces. So this is sometimes referred to as the monsoon being like a very large-scale land breeze. Have people heard of that idea before? Yeah. land breeze kind of model. So that's pretty common, you'll come across it a lot, but it is being sort of re-evaluated a bit in more recent research. I think there's no controversy about the role of the Coriolis effect. Obviously, when we have winds crossing, for example, in our summer monsoon, we have outflow from the Asian monsoon, and as it crosses the equator, we have that rotational component due to the Coriolis effect, which ends up being the northwesterly Australian summer monsoon circulation. And thirdly, we know that once the monsoon circulation is underway, once we have deep convection, a latent heat release, that is an important ingredient in strengthening that circulation. But I'll just go back here for a moment. Recent work has questioned whether there is a direct relationship between the strength of this temperature gradient between the ocean and the land. Because actually, if you look at it in some detail, you find that there are times when the monsoon's stronger, but the temperature gradient is actually weaker. And so that can happen on shorter timescales because you have more rainfall, more clouds, you actually have cooling over land. And it can also be the case if you look at climate change timescales. You find that the temperature gradient, as the monsoon becomes stronger, the temperature gradient may actually not be strengthening, it may actually be weakening. And so motivated by this idea, I guess, or this sort of re-evaluation, more recent work has put forward the idea that instead of being a kind of a very large-scale land breeze, the monsoon actually may be thought of more as a tropical convergence zone, which is, so if we have a classic ITCZ, the intertropical convergence zone, we know it's located close to the equator. It sits over the peak sea surface temperatures, typically, and migrates with those. But then the idea is that the monsoon is a tropical convergence zone which is pulled further poleward by that warming over the continents, and it actually sits over high most static energy, which is, I guess, associated with, for example, that location around 30 degrees north in the case of the Asian monsoon. So there's an interesting paper by Gadgil which talks about this, and then also a very nice review paper by Ruth Geen that you can have a look at if you want to find out more about this idea and this discussion. So I'll just very briefly spend a moment talking about each of the regional monsoons so that you know what I'm referring to. We talk about the Asian monsoon as this whole regional Northern Hemisphere monsoon, but then it can be considered to have a number of different components. In particular, the Indian or South Asian monsoon, as I'll refer to it, and then the East Asian monsoon, which sometimes also is considered to include the West North Pacific monsoon that has that sort of oceanic component as well. So I'll mainly just refer to the South Asian and the East Asian monsoon as those two regional monsoons. And there are some important differences between them. The South Asian monsoon is much more strongly forced by that meridional temperature gradient between the ocean to the south and the strong heating over the Tibetan Plateau, over the land in the summer. So it has that much more sort of classic north-south circulation and north-south temperature gradient. Whereas the East Asian monsoon is a bit more complicated. It has both that north-south gradient, but it also has a zonal gradient as well with the adjacent ocean. And it tends to have a weaker and more complex circulation, which also includes rainfall along the subtropical frontal zones, which are found in the ocean. The Mayu and Bayou front is sometimes considered to be part of the East Asian monsoon circulation. So that's probably a topic for a whole other lecture, but I just wanted to mention those distinctions here. Now to mention the West African monsoon. This is a Northern Hemisphere summer monsoon which follows pretty closely the classical monsoon criteria, where we have during the summer, like at the moment, we have these kind of moist, southwesterly winds coming into the intertropical region, so it's known as the intertropical front in this case, or intertropical discontinuity, which is basically that boundary between the moist monsoon flow and the much drier, hot northeasterly winds that sit over the Sahara. And so that's what happens in the summer monsoon season. And then the other season, we have these much drier, warmer, they're called harmattan winds that come down in the winter season. So that's pretty kind of classical summer monsoon in the West African region. There's a lot of really fascinating dynamics associated with this monsoon and the way that it leads to African easterly waves, for example, in this region, but I don't really have time to go into that now. The American monsoons are a little bit more controversial, so they don't match that classic definition of the monsoon with the wind reversal in terms of a complete switch in direction between summer and winter, but they do have a very strong wet season and dry season, and so that's why they're often included in our understanding of the global monsoon. So in the case of North America, there is a region of heating over land, the Sonoran region, the Sonoran Desert, heat low, and then there's moisture drawn in from the Gulf of California and the Gulf of Mexico and the tropical Pacific. And you can kind of see that, that red arrow there showing the direction of moisture transport associated with the North American monsoon. And then in the case of the South American monsoon, there's actually moisture coming in from the tropical Atlantic and also the Amazon River basin as well. So that monsoon is quite sensitive to the moisture transport processes over the Amazon basin. So we typically do include the American monsoons in the list of regional monsoons, but as I say, they don't quite meet the Ramage classic definition. The Australian and Asian monsoons are usually considered to be part of an interconnected system. So we have the strong summer monsoon in the northern hemisphere and an outflow from our region in winter. And then in our summer, there's the outflow, particularly from the East Asian monsoon, which drives the strong cross-equatorial transport and contributes then to the onshore flow over northwestern Australia during our summer monsoon season. So this southern hemisphere part is sometimes called the Indo-Australian monsoon or the Australian maritime continent monsoon, and sort of groups together this whole region from Indonesia, New Guinea and Timor and so on, and northern Australia into one. But for those of you who have worked on that region or have lived in that region, you'll know that it's actually very complex. And so it's quite challenging to really summarise what's happening in that region as a uniform story. And I'm going to focus mostly on the Australian part, even though there's a lot of interesting research that needs to be done and is being done on the maritime continent part of the monsoon. So I'll pop on now to talking a bit more about the Australian monsoon, just introducing it to those of you who are not so familiar. It tends to peak around January in terms of the large-scale northern Australian rainfall and active monsoon season. But the onset of the monsoon is usually defined around Darwin as occurring in late December. It does depend a lot on which definition you use, and there's quite a number of definitions that have been applied to the monsoon onset. We tend to see that around late December, January and February, and then we'll see the retreat of the monsoon by March or April as it moves back to the north. And so we define the monsoon shear line, which is the line separating westerlies from the trade wind easterlies. Maybe you can see the vectors there, or maybe not, but it's the red line. And then slightly to the north of that, we have this region of maximum convection, maximum precipitation, and it's easily identified in the OLR, the outgoing long wave radiation, which measures the cloud height. So basically we have very intense convection over that region. That's the ITCZ. So yeah, the ITCZ can also be identified as the region of strongest convergence of the streamlines, precipitation or lowest OLR. And the monsoon shear line, sitting slightly to the south of that, is co-located with what we define the monsoon trough, so low pressure, and maximum cyclonic shear. So you can sort of see that in that region. Okay. So let's just have a bit of a look at how the monsoon evolves over the typical season. So prior to monsoon onset, this is usually in December. The figures I have here are examples from one particular year. In January, I guess the monsoon was a little bit late to get going that year, but normally we'd see this more in sort of November, December. So you start to see the development of these heat lows over northern Australia, in particular this Pilbara low over in the west, and also sometimes what's known as the Cloncurry low over in Queensland. And sometimes they start to join and form sort of zonally oriented heat trough over the entire northern region through this period. But these tend to be only shallow features in the period before the monsoon circulation. So they're only around 1 to 2 kilometres deep, and they tend to be associated with relatively isolated clouds and thunderstorm activity during that build-up season. And it's not yet the full monsoon circulation. So we can see in the 900 hectopascal vorticity here and the mean sea level pressure contours, exactly the same period. So we're looking at this build-up time where we begin to have a shallow westerly flow over the north, and it's starting to moisten, precondition the atmosphere for the onset of the monsoon. And I haven't actually spent much time up north in that season, but I understand it's quite uncomfortable in the build-up with high humidity and so on. Some people are nodding, yeah. And then the monsoon season begins. And now we have the clearly defined monsoon trough to the north here, which has shifted over the land area, okay? So we have much stronger heat lows, and these are associated now with much more intense deep convection and much more widespread rainfall over the north by this time. And often we find tropical cyclones as well embedded in that monsoon trough. So if you've got keen eyes, you might spot TC Jim up here sitting in that monsoon trough as well. So the active monsoon is associated with widespread deep convection, a deep low typically over this Kimberley region here, which drives that northwesterly winds bringing moisture into the monsoon. And it's really how strong and how consistent that feature is that determines a lot of the strength of the monsoon itself. So work by Wosel Drozdowski at the Bureau, he's one of the long-term researchers of the Australian monsoon. He defined the active monsoon as when we have mean westerlies up to 500 hectopascals and then mean easterly winds above at 300. And you can sort of see this figure here showing that strong westerly flow now associated with the monsoon season. Okay. So that's a bit of an overview of the monsoon, but there's also a lot of variability, and that's one of the things that makes the monsoon really fascinating, and I'm guessing also one of the things that makes life hard for forecasters up in Darwin. In the case of the Australian monsoon, which I'm focusing on here, but other monsoons have similar kinds of burst-like behaviour and intra-seasonal variability. So bursts are these periods of above normal convective activity and enhanced rainfall. And breaks are the periods where we have low rainfall within the monsoon season. So it's not the dry season, it's a break between these burst periods after the monsoon has started. These figures come from an old book chapter, I think, or paper by Matt Wheeler and John McBride, and they're showing, it's very high, they're showing the outgoing long-wave radiation seasonal cycle over this large area with the variability for 3 particular seasons, 82, 83, 83, 84, and 84, 85, just as an example. And you can sort of see that there are these periods of relatively low OLR, and those are associated with the monsoon bursts. And then underneath that is the rainfall averaged over this top end box. And so now you can see that there's quite large rainfall totals associated with those burst periods. And the onset of the monsoon is shown here as these little arrows. I think they applied a couple of different definitions, which is why there's more than one arrow for each year. And you can see that that tends to co-occur with one of the first of those strong bursts. So we've got burst and we've got the monsoon onset around that time around mid to late December. So I got this figure from my postdoc, Hannah, who's working on this topic at the moment, and it just shows you a bunch of different years starting in 2000 up to 2022, 23, and it's just the northwest Australian region now. And the yellow bands are places or times where we have identified bursts based on a criteria of exceeding a 7 millimetre rainfall anomaly, and I think there's some, like it has to persist for several days as well. And you can sort of see just by looking at that there's actually a really remarkable amount of variability from one year to the next. So we have some years where there's like burst after burst, and then other years like 2018-19 where there was actually no identified rainfall bursts at all. There was almost a complete failure of the monsoon rainfall in that year in the northwest. Actually, there was a very heavy rainfall event in the northeast that year, which you may have remembered, with a lot of flooding and unfortunately a lot of deaths of cattle in the Queensland region. But in the northwest, really a complete failure of the monsoon that year. So understanding what drives this interannual variability, and I know some of you at Monash are working on some of these questions as well, is really, I think, really important. One of the drivers, although not the only one, is the Madden-Julian oscillation. And I understand Claire spoke to you about this yesterday, but it's that 30 to 60 day oscillation in tropical rainfall and circulation that passes through the region, the North Australian region and the Maritime Continent region, and brings with it, enhances, I guess, the circulation, the monsoon intensity, and potentially drives some of these bursts. So there's work by Hendon and Liebman, and then more recently Gareth Berry and Michael Reeder did some interesting work looking at some of the drivers of bursts. And there was a contribution from the active phases of the MJO in that region. There's also links with tropical cyclone development as well, and other rainfall features in the region. So just to look at the MJO phases, these are the 8 different phases of the Madden-Julian oscillation as defined by the standard indices, Wheeler and Hendon indices. And you can see here phase 5, 4, 5 and 6 are bringing, 4, 5 and 6 are bringing very active conditions, strengthening the circulation and bringing increased rainfall to Northern Australia. And we know that this is just the average conditions. Actually, every MJO is different, and there's also sort of interactions with other modes of variability that can alter this kind of pattern. But typically we do see that link between bursts and the active phases of the MJO. On longer timescales, we see variability in the monsoon associated with ENSO. So in particular, we see that in the northeast of Australia, we have overall drier conditions from October through December during El Nino years. And you'll note that that's not the peak monsoon, that's more the pre-monsoon and then the early part of the monsoon. And so it's associated with a later onset during El Nino years. And these are the typical onset dates of during neutral years, not of the monsoon itself, but of the northern wet season, which is sort of related to that. So you can see that it's normally, around late November, early December for the northern wet season, but during El Nino years, that can be substantially later. And so simply by pushing back that onset date, we have a less rainfall overall in that part of the monsoon season. And I guess we can try and understand better what are the features of the circulation that are actually pushing back the onset date of the monsoon. It is important to note, though, that the ENSO response is quite different, firstly in the northwest versus the northeast. There's been quite a lot of work showing that there's generally a stronger connection with the Pacific in the northeast than the northwest, but also there's quite a big difference for the so-called Eastern Pacific El Nino type versus the Central Pacific type. So you've heard of these different flavours of ENSO. Eastern Pacific is a classic kind of ENSO, and then these CP events have the warming closer to the centre of the Pacific and the date line, and tend to have overall stronger relationship with Australian climate and rainfall. But we find, for example, in the northwest, that if the El Nino is an Eastern Pacific one, we see pretty much drying throughout the seasonal cycle. So here are the months, and here's our rainfall anomaly. But if it's a CP, we actually expect to have slightly wetter conditions in January and February, but drier conditions in the other months. So this is becoming a more complex picture now of how ENSO is interacting with monsoon, and we need to be able to sort of understand, I guess, how weather systems and processes are actually contributing to these quite different responses between CP and EP El Nino events. On longer timescales again, we need to also think about the Interdecadal Pacific Oscillation, or IPO. So this is, I guess, modulating the position of the Walker circulation, where it's basically shifting eastward or westward, and therefore the strength of the teleconnections between the Pacific climate and Australian climate and Northern Australian climate are altered. It also impacts the position of the South Pacific Convergence Zone, which tends to be sort of dynamically linked to rainfall over southeast Queensland in particular. So during positive IPO, which is like an El Nino, where we have warmer Eastern Central Pacific SSTs on average, we see a sort of overall drying, but also a weakening of the connection between the Pacific and monsoon rainfall, whereas negative IPO, we see a stronger connection, wetter conditions, particularly in the northwest, and sort of a strengthening of that dynamical relationship between the Pacific and the monsoon. And so this can also complicate attempts to identify long-term trends, because if you only have a relatively short record, you may think you see a trend, whereas in fact it's actually related to some kind of multi-decadal variability. So finally, I wanted to talk a bit about monsoons and climate change. And firstly, I just wanted to start with the observed trend in the Northern Australian region again. And here we have a very interesting pattern of a statistically significant wetting trend in the northwest over the period from around the 1950s, or particularly since the 1970s onwards. And this has attracted some attention, perhaps the idea of moving agriculture and farming to the north as other parts of Australia become drier. But obviously, it's only a good idea if we know that this trend is likely to continue. And so there's been a lot of research to try and understand what may be driving this trend, and whether it's actually linked to anthropogenic warming or not. One recent study by Alex Broviak at Melbourne Uni, who's a CLEX PhD student, looked at changes in the frequency of these enhanced MJO phases. So remember, there was the 4, 5 and 6 were those phases where we see enhanced rainfall. And he was finding a positive trend over the period of this rainfall increase in the enhanced phase. And so he was arguing that that was a possible explanation, although I guess that raises the question of what is driving that MJO trend itself. Another separate mechanism has been put forward by a couple of studies arguing that changes in aerosols, or increased aerosol cooling over the Asian region, may actually be, whilst it's causing drying potentially over some parts of the Asian monsoon, may be causing an increase in rainfall for the Australian summer monsoon. So work by Raktima Day, for example, here, comparing model runs where we have greenhouse gases only, and you can see that Here we have drying over the north. This is for the historical period versus model runs where we have anthropogenic aerosols included, and that shows a positive anomaly over northern Australia. Perhaps is suggestive that that may be an important contributor. And then another study by Nora Fahrenbach, working with Tim Cowan and others, has also sort of suggested that aerosols may be playing a role. So more generally, if we think about the different processes that contribute to the response of the monsoons to a warming climate. This is a cartoon from the 5th IPCC report, and I think it's quite a useful one just to summarise some of these ideas. So here's our present day monsoon circulation with a number of different factors that influence the strength of the monsoon. And then if we think about, firstly, in a warming climate, we have an increase in atmospheric moisture, water vapour, so we have an enhanced onshore moisture transport. So that could potentially lead to higher monsoon rainfall. We also have changes in the circulation, and these are a bit more complex, but possibly an overall weakening of the circulation as a kind of dynamical compensating factor for the enhanced moisture transport. We end up with a weakening of the dynamical part, perhaps. We may have land use changes and also these aerosol changes which could be causing cooling over land in some regions that may be reducing the strength of that temperature gradient, if you think that's what's important for monsoons, maybe weakening that circulation. Or even land use changes as well in some regions with agriculture and land, forest clearing and so forth may also have some effect. So there's a lot of different processes that we need to think about here. And I always find it useful just to go back to the basic idea of decomposing changes into a thermodynamic and a dynamic component. So these are my only equations for this entire lecture, good or a bad thing depending on your preference. But basically we're looking at the balance, the moisture balance at a particular location in terms of precipitation minus evaporation is equal to the convergence of moisture in the overlying atmosphere. And just take the integral over that. We've got the horizontal wind vector here and the specific humidity. Now this goes back to work by Richard Seeger in 2010 and also of course Held and Soden in 2006. But the version that I'm presenting here actually comes from a more recent paper by Natalie Burles and Alexei Fedorov. So the main point is that as the climate warms, we would expect that there is a change in the moisture component associated with an increase in specific humidity. So this is the thermodynamic part. Then we have a change in the circulation, which is associated with this horizontal wind vector V, which is the dynamic part of the change. And then we have some cross term here. And so we can calculate this kind of moisture budget in a number of different ways. This is just one way of representing it as we think about a warming climate. And if you take a large area average or a zonal mean over the tropics, for example, you tend to have a strong effect from this thermodynamic component. But if you start to look at regional scales and things like monsoons, the temperature gradients become more important, and that's where this dynamical component comes into play. And so just a couple of examples here where we tried to apply slightly different versions of the moisture budget decomposition to climate model projections for Australian monsoon region. On the left is an older study from Arel Moiser in 2012 where we had the older CMIP3 models. And you can sort of see the total rainfall change in those models was actually a slight increase over the northern Australian region. The dynamic change in that version was very much a drying, but then a thermodynamic wetting was kind of overcoming that to give us a net increase in that particular set of models. A more complex moisture decomposition was put forward by a colleague, Robin Chadwick, who works at the Met Office, and he actually added in, so we've still got a thermodynamic and a dynamic one, which is basically just the mean circulation change here. And you can see that they're almost exactly opposite. So the mean circulation change is sort of balancing out, is causing drying as the monsoon and this convergence weakens, but the thermodynamic part is causing wetting. But then he added in this dynamical shift term, which basically takes into account where you have changes in the gradients. And so you have, the convergence zones are slightly displaced from their mean position in the present day. And that shift term turns out to be the most important for explaining the pattern of rainfall change in the models. So unfortunately, that means that future changes are very sensitive to the pattern of sea surface temperature change. And anyone who has been working with climate model projections will know that that's something that our climate models do not agree on. And so it means that we have a lot of work to do to try and constrain that uncertainty. If we look at the projections of regional monsoons, this is from the latest IPCC report, we have a lot of little boxes here for low, medium and high emissions for near term, mid-term and long term, and these are each of the regional monsoons. So you can see, for example, the South Asian monsoon, the overall projection is for wetter under all scenarios and all timeframes, particularly strong under the high emissions at the end of the century. When we come to the Australian and Maritime Continent monsoon, we can see again an overall wetting trend here, but note that I showed the box for that monsoon, including both the Maritime Continent and Northern Australia, and it tends to be that the Maritime Continent signal is much larger and much more consistent, and that kind of dominates. And so it's really a Maritime Continent change that we're picking up here. If we look at Australia itself, in the Northern Australian region, in CMIP5 and CMIP6 models, we find a very uncertain story. So climate models, half of the models that we looked at in CMIP5 and CMIP6 projected an overall drying over Northern Australia, and the other half, more or less, projected an increase in monsoon rainfall. And this is under the high emissions scenario, so it's really hitting it with a lot of warming, and even then we have this disagreement. And so I guess I just wanted to end with the fact that there's a lot of further research needed to try and constrain this uncertainty. The Australian monsoon is particularly a tricky one because the circulation is not as strongly driven as, for example, the Asian monsoon. It's got a lot of different drivers in the region, and our models in this part of the world are very sensitive to sea surface temperature patterns of warming and also to biases in our model SSTs. So there's a bunch of interesting questions for future research. I'm excited about the new centre getting into some of these, looking at sub-seasonal timescales, things like bursts and breaks, and how well they're actually represented in our models. What kind of weather systems are there in this region that actually drive this variability? Can we simulate them with a higher resolution model? Can we actually get down to the scales like you was talking about this morning that do a really good job of resolving some of these processes? What is driving these longer term trends that we've seen already? How will the monsoon change in the future if we have better models? Do we start to see a more consistent story, hopefully? How sensitive is the change to emissions pathways? Does it matter if we have a strong warming or a sort of weaker warming with a larger aerosol effect, for example? And finally, I'm also excited to look at things like net zero and stabilisation pathways, which my PhD student Rita is going to be working on, because I think it's important to understand that there may be some aspects of the monsoon which are quite non-linear as well in their responses to warming. So that's all I wanted to talk about, I think. Yep. And please feel free to get in touch if you want to discuss anything to do with the monsoon, and particularly the new research projects in the new Centre of Excellence, which will have a focus, some of the research will be focused on this topic. Thank you.